All right, so this is answers to FRQ cumulative assignment part A. This is for problem 1. There are 4 runners on the new high school team. The team is planning to participate in a race in which each runner runs a mile. The team time is the sum of the individual times for the runners. Assume that the individual times for all runners are independent of each other. This is actually really important. We'll talk about why later, but I do want to make a note of it. The individual times and minutes of the runners in similar races are approximately normally distributed. That's a key word. With the following means and standard deviations. You may assume that team race times are independent of each other as well. Okay, so the independent thing. Basically, the runners' times are independent, and if they ran multiple races, the races are independent. Not sure if that's really true, but they're claiming that's true, and ultimately that's going to be important in a little bit. So, here are race times, average 4.9 minutes, 4.7, and etc. And here's the standard deviation in times. Runner 3 thinks that he can run a mile in less than 4.2 minutes in the next race. Is this likely to happen? Explain. So, his expected time is 4.5, or on average. This is what our mean is. And he thinks he's going to run it in 4.2 minutes or less. Right? So that's what we're looking for. So let x equal the number of minutes it takes to take runner 3. And we should note that because it's a normal, we know we're going to be working with a z. Matter of fact, as soon as you tell me anything's normal, I'm writing that down and go, I'm starting there. That's my starting point always. So we want the probability that x is less than 4.2 minutes. Well, I'm just plugging in 4.2 for the x, 4.5 for the mean, and 0.14 for the standard deviation, which just came off the table. All right, so then I'm going to use a calculator, and there's 2 ways to do this in a calculator. I'm only going to show one of them. I'm going to kind of do the shortcut. It's going to be stats test and just the z-test. And in this case, my mean was 4.5. My standard deviation was 0.14 for runner 3. My x is 4.2. And my sample size is just 1 runner. So my sample size is size 1. And I want to know the probability that he can be less than that. Well, when I calculate this, I end up getting a z-score of negative 2.14 and a probability of about 0.0161, which is not really likely. It's less than 2%. I think it's pretty unlikely. The dude is obviously deluded and likes to brag. So or lady, maybe. Anyway, I don't think it's likely that the runner is going to do this in less than 4.2 seconds. But it could happen. The next thing, the distribution of possible times is approximately normal. What are the mean and standard deviation of this distribution? Well, they tell me the mean is 4.9 for each runner. So basically, how long do I expect him to run it? Well, I just add them all up, and I can just add the means directly. And so I would expect, hey, based on those times, I'm expecting it to take 18.9 minutes. That's what I would anticipate. That's the mean. That's very easy to do. Well, they want me to do the same thing with standard deviations. Well, a couple things. First off, the distributions must be independent. If they're not independent, I can't add them. So that's why earlier when they told us there were independent times for the runners, I needed to know that. So that's why that was important. Now, as you may remember, we cannot add standard deviations directly. We can add variances directly, so we square the standard deviations in order to get a variance. So we square the standard deviations in order to get a variance, and then we can sum that. So we have the first standard deviation, 0.15. So this is runner 1, runner 2, runner 3, runner 4. We square those, made them into variances, and we sum them. And we take the square root of that, and we find out that the standard deviation for the team is 0.3003. So we squared them, summed them, took the square root of it, and that gave us the standard deviation of the team. All right, so suppose the team's best time to date is 18.65 minutes. What's the probability that it'll beat its own best time? Well, once again, We know we're working with a normal. We know what the mean is. We expect them to run this in 18.9 minutes. But we want to know the likelihood that they can do it in 18.65 minutes. That's what we're looking for. All right? So, stats test, z-test, 18.9 minutes. Standard deviation is 0.3003 that we calculated. 18.65 minutes. Now, I need to talk to you about the sample size. You're sitting there going, hey, there's 4 runners. And I go, yes, there are. You're correct. But this is the team time. This is the team standard deviation. This is the team time we want to beat. And how many times are they running this race? The team is running the race 1 time, so our sample is a size 1 this time. If they'd ran the race multiple times, then the sample size would have changed. But in this case, they're only running it once. So we end up with a standard deviation, or a z-score, I should say, of negative 0.8325. And we find out there's about a 20% chance, a little over 20% chance, that they run this race. The team runs a race faster than their fastest time. So it's not that unlikely. All right. So then it says, given your calculation in part C, what's the probability that the team runs the race 20 times? At least one race is faster than 18.65 minutes. So now we're running it 20 times. So we have a fixed number of times. Then we have this other phrase, at least one. All right? That means 1 times fast, if 1 times faster, that satisfies 2, all the way up to 20. So basically, we go, you know what, we could have 0 successes or we could have up to 20. This is what I'm looking for. Notice I circled up to the right. And whenever we have that phrase at least, we should be thinking 1 minus. Well, it's 1 minus the largest number we're not interested in. So 1 minus the probability of 0. All right? So 1 minus the probability of 0. Now, because we have a fixed number of trials, we have a fixed probability that we just calculated, 0.2025, and trials are independent, this is a binomial. All right, so this is the binomial, and I can do a binomial PDF of 1 plus a binomial PDF of 2, all the way to the binomial PDF of 20. And that might be a good way to show your work. I'm going to discuss 2 ways to show your work here. All right, 2 ways to show your work. You only need to show 1 of them. Please start off by writing your formula. By writing your formula, you're telling people, I know it's a binomial. All right, and then you're going to plug in. Well, if you're doing the PDF of 1, this is the PDF of the first one, but then I need a PDF of 2 and a PDF of 3. So I'm just going to use the plus ... and then I do the PDF of the last one. So that would be work shown, and if I did it this way, that's full credit. Now, the way I prefer is working with the 1 minus. 1 minus the probability of 0. So 1 minus this, and remember, whenever you're working with multiple values, you're using the CDF value on the calculator. So since I have multiple possible answers, I'm using the CDF. All right? So 1 minus 22, and this is the probability of 0, so let's do this now. 1 minus second vars, binomial CDF, trials is 20, P is 0.2025 because we already calculated that earlier, and X is 0. And we end up saying, you know what? There's about a 99% chance that if they run it 20 times, at least one of those will be faster than their fastest time. Now, some of you are going, hey, you know, Mr. Spencer, you said to use a CDF because we have multiple values. Well, we only have 1 here, so could we have used a PDF? This is a special case when you could have used a PDF and you would have gotten the exact same answer. But generally speaking, I much prefer you just go, anytime you have multiple values, which you have multiple values here, use a CDF. If you go about that way, then anytime you have multiple values, use CDF, you'll be good to go. You'll get this right. All right, moving on to the next problem, or the next part of this problem, because it's long. All right, part E. Given that the probability that you calculated in part C, what if the team runs the race 20 times? What's the probability that more than 5 times are faster than its fastest time? So we're going to run this thing 20 times, and I want the probability that more than 5. Well, more than 5 would be 6, 7, 8, 9, all the way up to 20. So I have more than one value, so I know I'm working with the CDF. All right? Once again, and I said use the probability we calculated in part C. Well, that probability we calculated in part C was the 0.2025, because that's the probability that they run the race once and do so faster. What's the probability? And then here we were going, hey, we run it 20 times. What's the probability that we have 6 or more that are faster than the 18.65? So we want the probability is greater than 5, which is the same as saying the probability is 6 or more. Because it's a binomial, we have a fixed number of trials and a fixed probability, and they're independent. We write this down, we let people know that we know it's a binomial. 2 different ways to show this. All right, I can show the probability of the first one and the probability of the last one that satisfy, which is the 6 and the 20. And I'll put a bookend mark, I'm good to go. That would be work shown. What I prefer is what I put into the calculator. What I put in the calculator, because the calculator works left to right, I subtract it, and it's a more than, I go 1 minus what I don't want. What the highest number I don't want is 5. So in this case, 1 minus second vars, binomial, CDF, trials is 20. Our probability is 0.2025. X is 5 because that was the largest value that I didn't want. Press enter. And something went wrong. Second vars, binomial, CDF. Do that again. Oh, I forgot to change the X value to 5. And so, and I need to do the 1 minus. So let me do that one last time. So 1 minus, I'm sorry about the mistake, second vars, binomial, CDF, 20 trials, P.2025, X is 5. There we go. So about 20%, a little over 20% chance that if they run it 20 times, that they'll have 6 or more times that are faster than their fastest time. So if they run it 20 times, we think there'll be about a 20% chance that there's 6 or more times that they'll run it faster than their fastest time. Using your calculation in part C, once again, we're referring to the 0.2025. What's the probability that their first time to run faster than 18.65 is their third time to run the race? All right, so couple key words. First. If I see the word first, not always the case, but 90% of the times this is a geometric. And they want it to happen on the third time. So basically 1, 2, 3, all the way to infinity, it needs to happen on this specific event. I want my third one to be my first success. That means I need 3 blanks. This needs to be a fail, this needs to be a fail, and this needs to be a success. So the probability of success is 0.2025. The probability of a fail is 1 minus that. But I needed 2 fails, so I have to have it twice. This right here would qualify for work shown. And the fact of the matter is, you can just multiply that out on your calculator by hand. If you want to use a shortcut on the calculator, you go second vars, geometric, PDF. And here's how I know it's a PDF. There's only one value selected. So 0.2025, X is 3. And so we end up with 0.1288. So almost 13% chance that their first time to beat their fastest time is on their third time. So basically, the first time to beat their fastest time occurs on a third time. There's about a 13% chance. Hey, this is getting old. Use your calculation in part C, 0.2025. What's the probability that the first time to run faster than 18.65 occurs after the fourth race? So they're saying, hey, you know what? What's the probability that X is greater than 4? So I'm looking for 5, 6, 7. Here I'm looking for multiple values. So this probably implies a CDF. I see first, and first implies I'm probably going to be using a geometric. So because the geometric goes on to infinity, I can't just sit there and go, what's the probability that it happens on the infinitieth time? Because it's probability 5 plus the 6 plus the 7 plus the 8 plus the 9 all the way to infinity. I can't do that. So I have to do a 1 minus. So 1 minus the largest value I don't want. The largest value I don't want is 4. Well, that means probability of success here, probability of success on the second, which means a fail on the first, and then ultimately probability of a fail, success for the third, etc., which means on the fourth, I have a fail for the first, a fail for the second, a fail for the third, and then a success on the fourth. Now, that's actually a lot of work to do by hand. And once again, this would be good work shown. That's good work shown. So 1 minus second vars, geometric, CDF, P is still 0.2025, X is 4. You know what? I'm going to start over on that. 1 minus second vars, geometric, CDF, P is 0.2025, X is 4. And we get 0.045. So there's about a 40% chance. So they're saying about a 40% chance that it's after their fourth time running, that it didn't occur during the first 4. It occurred after the first 4. All right? Which means it's almost 60% chance it occurred among the first 4. All right? Using your calculation of the part C, well, we already know they're referring to the 0.2025. What is the probability that the first time that they run faster than 18.65 minutes is during their first 5 races? All right, during the first 5. That means I'm interested in these values. That's great. I don't have to do a 1 minus. And by the way, I have more than one value. So this indicates CDF. First tells me I'm probably looking with a geometric. So I need the probability of success on the first, success on the first, or success on the second, which means a fail on the first, all the way to success on the fifth, which means fail on the fourth, fail on the third, fail on the second, fail on the first. All right. Once again, that's kind of a lot of work. Yes, you can do this by hand. That's kind of a lot of work, and the calculator is really friendly on this. Notice I'm not working with the upper right-hand part, so I don't need to do the 1 minus. So I can go second vars, geometric, multiple values is a CDF, and our X value is 5 in this case. And we end up getting 0.6774. So there's about a 68% chance that the first time they run faster than their fastest time would occur during their first 5 races. Lastly, what is the probability that if the team runs the race 5 times, that their mean time for those races is faster than 18.65? Wow, that's interesting. We're talking about a mean. As soon as you talk about a mean, I start thinking, oh, you know what? Probably going to be normal. It's like, oh yeah, I remember that. The distribution was normal. They told me that my mean time was 18.9. They want to know 18.65. And this is very similar to what we've done before, But now we know instead of X, we're working for X bar because they said mean and we're running multiple races. So consequently, I'm using this formula where my sample is size 5. So plugging in, this is the X bar, this is the actual mean, this was the standard deviation for the team speed, team standard deviation, and this is the sample size. So stats test z-test 18.9 for the team mean, 0.3003 for the team standard deviation, 18.65 for the average of the team, and they're going to run it 5 times. When we do that, if you don't hit the button too many times, and I did, so there's about a 3% chance. There's about a 3% chance that the mean time for 5 races will be less than 18.65 minutes. This was different than the first time we did it, where we said, what's the probability they'll run a race? So that's why the sample was size 1. Here we're doing 5 races. And once again, one of the key words that shows up is mean. All right? So hopefully that'll help with that. And I'm going to stop this recording, and thank you all for watching.